Right. Good morning, everybody. My name is Roland Bock. I'm head of development at Pro Financial Limited. It's a payment service provider and also a offering a prepaid credit card program. And I'm here to talk to you about reducing the spew that the compiler generates when you're dealing with templates sometimes. Because template libraries can be cool. They can do marvelous things. They can allow you to express complex topics very elegantly. But when you're doing something wrong, they sometimes tell you in a really bad way. And there was an article in 2010 by Eric Niebler, a friend of very clear words. And he says, the title is Why Template Errors Suck and What You Can Do About It. And he's giving a few guidelines of what you could do. And that got me started. And in this talk, I will cover the topics that he did in his article, plus a few more details that I use in my own library. The important takeaway, I think, is that there is not going to be a silver bullet, right? So it's not like, do this and you will never have bad template errors again, right? I think there is no such thing. And I will have a range of techniques that are easy to explain, hard to do, and hard to explain, still hard to do. Nothing will happen in all situations, again, but I think this could give you some ideas how to handle your own libraries or how to help other people improve their libraries. Okay. All the examples that I'm giving are from a library that I presented yesterday. It's called SQL++11. This is the only introduction slide, so I'm not going to repeat the talk, obviously. But it gives you an embedded domain-specific language for doing SQL in C++. Looks like this. So you have a select statement, right? And you have some table foo that has columns name and has fun. And so you can pretty much write normal select statements as you would in SQL. You can do that now in C++. Some where condition, and then if you give that to your database, then that will give you back a range of results, and you can iterate over this range, and the result types are friendly enough to mirror the names of the columns that you've introduced here, or the names of any kind of expression that you introduced here. And everything here that doesn't look familiar, like std_err or that isn't a keyword in C++ is templates. So this call operator of db is a template, the row is a template, select is a template, everything here pretty much is templates. So this is a really heavy templated library, but one of the most important aspects of the library is to give users reasonable errors in the error messages in the case they're doing something wrong. So this library really anticipates people doing something wrong because it's SQL, and every C++ programmer who's using SQL in C++ says, well, this is easy. I'm concentrating on the heavy stuff. So as a result, most people do really stupid mistakes when they're doing SQL, and the library is supposed to help them fix these mistakes. So it will tell you everything that you do wrong, and it has to do so in a reasonable way. Okay. But sometimes when users do something which is not anticipated by the author, in this case by me, still bad things happen. And this talk is about how to reduce the bad stuff. So in this case, I never anticipated that someone would be stupid enough to not put a table object in here in the from, but instead put a string there. And not having anticipated this, this results in tons of garbage. So 19 kilobytes for error messages in GCC and 92 lines, and a something which is rather rare in my experience. Clang gives way more, both in kilobytes and in lines, with this problem. That's the current master branch. In the development branch, this will go down to something which can be presented on one of these screens with techniques that I'm going to present. All right. So, but one thing that we've already seen by this example is that compilers make a difference. It really depends on what compiler you're using. So what compiler you're using tells you something or makes a difference when you look at the results from template errors specifically. So you should support compiler developers because it makes a difference. And the race between Clang and GCC has supported basically both groups. They are both improving on their error messages, and users should support them. You can have global impact if you support compiler developers, and I mean, not many people can say that from themselves. Right. Also, as I said, the master branch gives you like several kilobytes of data in error messages, but in the development branch, just a few lines. So the quality of code of libraries also makes a difference, and that's the main thing for this talk. So you should support library developers. You should, as Eric mentioned in his article, you should consider huge error messages as an error of the library, not as an error that you did, as an error of the library. So you should file bugs for those and help library developers to improve their libraries and to make all of our lives easier. So, what's the best way to avoid template errors? Well, the best way to avoid template errors is don't use templates. And I'm not kidding, even not in this talk. There are so many people using templates just because it's C++. And in C++ we use templates, right? And we want to use templates because it has to be generic. But many people just use it just because they can, and because it's C++, and because, well, yeah, they're so cool, and they want to be generic, and they don't really are, and they don't really need it. So many templates aren't really needed. Many templates are also not needed in your API. Maybe it's totally reasonable to use templates somewhere in your library code, but you don't have to expose them in your API. Okay? Maybe runtime polymorphism is completely sufficient. You don't need compile time polymorphism. And maybe you can hide your templates, like behind the API or also behind inheritance. That is something I'm using now for, I don't know, about a year. The definitions of tables that are used with this SQL library is done through templates. So there's, oops. This table T here, that's a template. Does some CRTP magic. It uses specifications for the columns of this table. It's a very big template and pretty complex. But all of this can be hidden by inheritance. And since if you're using this library, you would use a code generator anyway to create these specifications for those tables, you can write this small thing that represents the actual table through inheritance, just easy as that. Right. And the effect on error messages is for this little statement down here, where something is wrong. That is the error message if you don't hide the table template, and this is the error message if you do. Right? So that's, I don't know, maybe 2/3 still, but I mean, it does make a great effect, and if the expressions are larger, it can make much more effect. Okay, so hiding template is one. Another thing that you should always try to do is to try to avoid recursion in your template libraries. And I'm saying that because, well, all the introductions that I saw, at least, for Veridic templates say, okay, you have Veridic templates, you have to go through them one by one, through the arguments one by one, and do some recursion. You should try to avoid that, because recursion is slow. It's typically limited. You can change those limiters, but for instance, Clang has a stack limit of 250 by default, I think. GCC has a recursion limit of about 1,000 or so. So it's slow, it's limited, and it can lead to really dreadful error messages if something happens way down the stack. Right? And as an example, let's take a look at a Veridic all. This thing is a type that should yield true if all arguments that you give to it have a value, true, and otherwise it should yield false. Okay? And if you want to do this in the classic way that the tutorials tell you, then you will do something like this. You will have a closure for all that has no arguments. Well, if there are no arguments, then all arguments are true, obviously, so the whole result is true. And otherwise, you just take the first argument and compare that to the result of the rest. And so that's it. Okay, easy enough, right? Right. Now, let's use an example. We have true samples and false sample classes. One have a value of true, one have a value of false. We create an instance of this all and put that in a static assert and see what happens. And as you may have noticed, one stupid person entered an int here. So this is not going to work because int doesn't have a value. Right? The error message looks like this. That's annoying because it's such an easy thing. And still you get way more than one page of error messages for something really simple. So what you can do is you can, at least in this case and in many other cases, you can avoid the recursion. You can avoid recursion by doing something more clever than the introductory books tell you. So you can use a helper class that takes a bunch of bools, and then you compare the bool list filled with your own values to a bool list with the same number of values, but using the comma operator, turning all of these values into true. So you compare your values to something where everything is true, which is the condition that you want to check for, right? And you use is same to make sure that these two are same. And so you have no recursion anymore. It compiles way faster. Louis Dion did some comparison at CPP Now this year. It's orders of magnitude. It can use way more arguments. And the error messages, if you're doing something wrong, is like this. Compare that to the way more than one page that we had before, for even 8 arguments in this case. So avoiding recursion is something that is intellectually challenging, but can be really, really helpful. It's not always possible, obviously. All right. Now for something not so esoteric, maybe. Use static assert. I'm a big fan of static assert because, well, it gives you very specific error messages. You can say specifically what went wrong, not just depend on something the compiler generates for you. And for using static assert, I most of the time use this helper class. It is a class that takes any number of parameters and basically is always false. Only the compiler doesn't know that because the compiler has to think about, well, maybe there is a partial specialization for this. So it has to wait until this is instantiated. And in the library, there are also many sets, and this is one of the uses of static assert. If I want to join two typesets at compile time, I have to make sure that both types that I give to this joined set are actually typesets. So the default instantiation is, well, assuming that these are not typesets, and I'm just using this wrong T to static assert. Whenever this is instantiated, that, well, it tells the user that, okay, both arguments have to be typesets. And the golden path is, well, if you have typesets, then you can use partial specialization to say, okay, this is a joint set for two typesets, and then you can create the joint set. Right? So I think this is a good usage of static assert. Gives a very clear error message. In most of the cases, this particular one is only for the library developer, so for me, because if something goes really, really wrong somewhere in the library, then probably these typesets will also fail, and I don't want to have cryptic error messages. I want to have clear error messages like this one. Okay. Now I'm also using static asserts in functions, and functions are much more complicated. So what I'm doing here is the from method. So what we've seen earlier is this select something from something. This is the from method. There are actually two almost identical but slightly similar versions of the from method. So I have a from impl method which does most of the bulk work, including the static assert down here to check whether the arguments are really tables, because, well, if you have a from in a select, then the arguments should be tables, right? And we're using this all again here to check if all of these are tables, and if one of them is not a table or a join, then, well, we tell the user so. Okay. Now, if the user does something stupid and tells or uses an argument which is not a table, that is what we see here, down here. So select all of T from T alpha. Now T alpha, that is a column of a table, so it doesn't fulfill the requirements. That is also the message that we get, right? Static assert, at least one argument, blah, 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 is not a table. Okay. But then we see the call stack that, okay, this is coming from the call from the from impl, so that at least one element of the stack that we don't want to see as a user, because we don't care whether it is an impl or not. And what we also see is that the compiler just goes on after that. So it runs into this first static assert. That is a hard error. There is no recovery from this. But the compiler, like a beheaded chicken, just runs on and spills its mess, right? And so it runs into the next static assert, which has to fail because, well, the first thing is not a table, and then the next static assert will fail, and you're lucky if it fails in a reasonable way, because, I mean, if you're using a string, as I did in the very first example, then this will fail in much worse ways, because then not even the value that we check in the static assert will be calculated in the right way, and then all hell breaks loose. Right. So what we see is we should move, if we're using a static assert, we should move the static assert as close to the user as possible, because that is the way to prevent this. And we also see that, well, static assert is kind of ugly because the compiler just continues. That's bad, right. So what it didn't mention, right, static assert, if you have static asserts or any other kind of hard error in the return type in addition, then your static assert is too late. So because you have to enter the function body or the compiler has to enter the function body to get to the static assert. If there are hard errors in the return type, well, it's kind of too late because it's already evaluated, and it will tell you all kinds of crazy information about the return type that you're not interested in as a user, potentially. And then it will tell you that, oh, by the way, there is a static assert in the function. And then it will drone on and say, well, come on, there are way more mistakes here. So let's try different stuff. Enable if. Enable if is something that is very useful for partial specialization and for disabling stuff. It's also useful for disabling or enabling certain functions. And I don't really like the syntax, I have to admit. So, and it got better with C++11, so with the order and the trailing type name. It's nicer now, but still, I mean, in this example, it's 4 lines just for the return type. But let's see what it does in the compiler. Well, the compiler, if you're using Clang, is very clever. Clang, at least in version 3.5, recognizes enable if and can give you very, very precise messages about enable if, and this is the whole error message. So that's beautiful, right? GCC, on the other hand, I think this is GCC 4.8 or even 5.0, I'm not sure, doesn't do the special treatment of enable if, and it gives you horrible stuff, and nobody really wants to read this, right? So, again, compilers make a difference. Please support them. Please tell GCC developers to fix this. I'm not using GCC most of the time, so somebody else will probably have to do that. All right, so for this reason, I personally don't recommend enable if for something to reduce error messages. It's cool for all kinds of other stuff, but I wouldn't recommend it for reducing error messages. All right. And yeah, you could use a second overload. That's one argument that people make to produce the invalid case that does something that doesn't fail badly. But then if both overloads don't match, then you probably end up with way more stupid junk that you don't want to read. So I don't know. So let's take a look at the future concepts light. I really like that. That is beautiful, right? So it happens that I already have test classes to test if something is a table, yes or no. So writing a concept for something being a table, that is really easy in this library. And then we can use these table concepts in a template. So, and I really like this syntax. Of all the syntaxes which are available, I prefer this one. Still says it's a template, but it says, all right, we want table arguments here, and then everything is fine. It's a short, very clear notation. But the error messages, I have no idea. I cannot really tell you because, for one, in some of the recent feature additions to the prototype for concepts light and GCC, the formatting of errors got completely messed up. So it doesn't give you clear error messages anymore as of now. It will go back to that, obviously, but currently it gives you way too much details about what went wrong. And the other is with some code, like for instance with the code of my library, it doesn't really work. It yields an internal compiler error because it cannot handle variadic template methods, member methods in CRTB-based classes. Well, okay. It's a rare case maybe, but in my library it's the central thing. I cannot do without it. So as an intermediate summary that says, well, static assert is cool in the way that it gives you very specific error messages. But the compiler continues. Static asserts in the function body are too late if there are problems in the return type. Enable if is, in my taste at least, very ugly to begin with, and GCC gives really ugly error messages. Concepts light are going to give you nice code. They're going to give you really, really nice error messages, I'm sure of that, but they are not ready yet. So again, please support compiler developers to make this happen, because this is going to change our world. But now what? We still want to reduce our error messages. Now, my personal strategy is to see if we can fix the problems with static assert, because I really like those specific error messages. All right, so let's take a look at a simpler piece of code. This is part of the test framework for the library. It's a mock-up for a database. It has a call operator. The call operator is supposed to be given a statement, so one of these, select or insert or whatever statements, and then run the statement with this database. Right? So that's simple enough, and we have some sample code here. And what it does, it produces these error messages. Okay, it's not too bad. These are the complete error messages. It's already reduced a bit from what it was earlier on. Clang tells you the reason that the library developer decided to give. So it says that there is a where expression required, even if it's just where true, because, well, I believe that the probability that you just forgot to write the where expression is higher than the probability that you actually wanted to omit it in order to select everything. Again, that's a matter of taste, but anyway, it's the shortest example that I could do with this library. So this is the concrete error, right? And everything in between, so here the call side at the bottom and the error at the top, everything in between does not interest anybody except for maybe me, because I'm the library developer and nobody wants to read this stuff. But just for the purpose of this talk, let's still go through this. So what we see is at the bottom, that is our own call. It runs into what we've seen on the last slide, into this run function. That calls, the run function in the statement calls this result methods type that is a base class of the statement class, and calls the run method there. That calls check consistency on the statement, which already tells us that, well, something is fishy here because we're doing way too much ping pong between types, so statement to the results method type, back to the statement. Then in the statement, in the check consistency thing, you will see something. If you learn more about how to avoid avoid recursion, then you will recognize the swallow. The swallow is basically something where you initialize a vector of ints with a bunch of values that you don't care about, and use the similar technique as in the alt. You'd use a comma operator to make sure that it's actually an int. So this is already shortened from what it could be by avoiding recursion. And then one of these calls goes into the where statement, and the where statement somehow figures out that it hasn't been called yet and gives you this very specific error message. All right. Now again, all of this doesn't interest anybody except for the library developer. But how can we avoid all this? Well, obviously there are already calls to get to this point and check individual parts of this statement, whether they are ready to run or not. Well, we could rewrite these calls to something that doesn't directly lead to a static assert. We could turn those functions into something which yields a const expr true or false to indicate whether it's ready to run or not. And then we could use the all that we had in the beginning and collect all these true or false values at compile time, bring them together, and if all of them are true, then hey, yes, we can run. Okay, cool. and otherwise, well, we can't. Something's wrong. Okay? So that's still simple. Not going to show that in all detail, but the result would be something like this. The statement would have a run check type. That's basically the this all that we had, and that thing has a value, and we can just check whether the statement is consistent or whether it's ready to run or whatever. And then we have brought the static assert down to the user. Okay, that's cool. And it's really nice. If you take a look at the error messages, it says statement is inconsistent, directly above the line that shows that shows the code that we wrote ourselves. Okay, that is cool. But then, well, the compiler still drones on, because that's not going to change just because we did something cool. The compiler still drones on, still runs into this run method, still goes through all that stack and does all the same stuff again. Right? Okay, so that's annoying. We use something that is called static dispatch. That is ugly. That's one of those things that I really don't like, but I think it's necessary. There's no real way around that, as far as I know. Use static dispatch, where you use the type of this return value. So this run check is a return value for a meta function. You use this type as a helper argument in calling a helper function. So first you do the static assert, then you use the type of the run check, which is either a true type or a false type, and call a helper function. And the helper function has two overloads. One is with a true type, this one here. That is for the good case, so the statement is consistent, so we can actually run. And that does everything that the original function did, so it calls the run. And the other uses the false type, and we don't even have to implement this because this is not supposed to be ever called. It doesn't have to be linked. So we can just write this as a false type. This is going to be called if something is wrong and the compiler has nothing to complain about. All right. So if we do that, then this is our whole error message. So only basically 2 lines or 2 blocks. One is the error message that the statement is inconsistent. And the other is, all right, that is our statement that we actually used. Okay, so this is nice. It's short. But it's not very helpful, is it? I mean, if you're not a user of this library and haven't run into this problem several times, you will probably say, well, why is this inconsistent? I mean, it's a select one column from a table. That's cool. If you don't know the library and you don't know that the library requires a where as soon as there is a from, then you may even give up and say this library is stupid. Right? So we have to give the good error message. Right? So this error message that says a where clause is required for this statement. All right. But we don't want all that junk, obviously. So the solution that I'm using is instead of collecting all these trues and false, right? So these are values and or const expression values, and we can collect these values at compile time and throw them in an all. Instead of collecting values, we could actually also collect types, right? And then do some comparison on these types and decide what we do. And the idea is to have basically 2 classes of types. One is something like this. This is a very specific type for this case where you have a missing where clause. It contains a std false type, indicating that something is wrong here. It also contains a static assert with this wrong type that we had earlier on in the talk, where the compiler has to wait until this is instantiated to actually fire the static assert. And it says the exact clear message that we want to give to the user. And this whole thing is a type. And as long as nobody calls this static function, nothing will ever happen, right? The static assert will never fire. And we have a second type, that is the consistent case, that says, well, everything is okay, and the type is a true type, the function is something that will never raise any static assert, so that is cool. And what we do now is we, all of the clauses of this SQL library can decide on their own if they, for themselves, are ready to run or not. And then the overall statement has some additional checking to compare all the tables and all the types and see if there are some inconsistencies. And then we can take the types from all the clauses plus the statement itself, put them in some kind of type array, and then search through it, search for the first one which contains the value false. If that is existent, then we return that the same way as we returned a true or false before. And if there is no false type, then, well, the default case is the consistent case, right? So now we returned a type that contains first the information, whether it's okay or not, and the other thing is it contains a method that if we call it, it will fire a static assert with a very specific message. Right. So now it looks like this. We just call the static method on our run check type that either fires or doesn't. And then we continue with the same dispatch as before to prevent the compiler from emitting more follow-up messages. Okay, and now it looks like this. It's now one line more because there is one call to the static method, but that's not bad. Because in return for this one line more, we get now the very specific message. So this is a short, precise, and very helpful message to the user. This is what I personally want. Okay. Now, are we there yet? Not really. Because it may be the case that all our attempts to prevent errors from being shown in an ugly way may be thwarted by the arguments that the user gives. So if the T, for instance, is a string, then, well, a T doesn't have an underscore run method, so this decal type will fail. A T doesn't have a run check, so, and that non-existing run check obviously doesn't have a static method, so this will cause a static assert, this will cause a compile error before we even get to some static assert because that's not there. So, well, that's annoying, but it can be easily be solved by some template programming. Again, we can use a run check template method that first checks if the argument actually is a statement, and only if it is a statement, it will return that run check type. And if it's not a statement, it will return another type which gives the precise message that, okay, you have to give a statement here. You gave something different, right? And then that thing will have this static method and tell the user when it's called. All right, and in the return type, well, we use the false case in a different way. Now we don't return the normal return type, we just return something that won't ever fail, like in this case, a void. That's harmless. So this decal type with the run check meta function, which returns true or false, will either return the correct run type, the correct return type if everything is okay. Otherwise, it will return void. So this won't produce an error. This won't produce an error. Okay, so we're clean. Right. So for the scope of this library and for the scope of this talk, we're done. Right. And just to finish this up, the very simple mistake at the beginning which yield from something between 19 to almost 50 kilobytes of error messages. If we apply all this wisdom to this from function, it boils down to this. Right? So this is now the complete error message that was earlier on something between 19 and 50 kilobytes. Right? And it's the only thing that I don't really like about this is the way that Clang handles the follow-up errors, at least in my taste, it's follow-up errors. So we have this code that says select T alpha from T, so this is the error. This now returns a bad statement, and it tells me that, okay, there is no member where in bad statement. I think this should come below the actual error. GCC does it. GCC first tells me that this is the error, at least one argument, and is not a table or join and from. That is the very concrete error. And that is the code that I have. And GCC gives the message that we have at the top here, at the bottom, which is much more helpful, at least in this case. And Clang does this way. But anyway, this is a very short thing. And even if you continue with more methods here, so you have a having and a group by and a limit and a from and whatever, Clang will stick to this one more message, by the way. All right, so that's very short. In summary, all the suggestions that I made is support compiler developers, that's really important. Support library authors, again, that is really important. You can make a huge impact even without writing libraries yourself or without writing compilers yourself. You should, in general, in my opinion, try to minimize the number of templates that are exposed to the users of your code, because most of the time, or in many cases, they don't really need it. You should try to minimize recursion. It's not always possible to get rid of it, but in many cases, you can just avoid it. You should do parameter validation at the API border, not somewhere deep inside your library. It should be close to where the user is, because otherwise the user will get all the stack between that. And my personal recipe at this moment is using static assert, at least for functions, and most of the stuff that I do are functions. Wrap return types in the way that I've shown so that you cannot fail in the return type. If you fail in the return type, it gives you horrible error messages. Use static dispatch to prevent the compiler from just carrying on after you know it's wrong. And use these portable static assert to not only give a generic message. I mean, if generic messages are what you need, then you don't have to use it. But if you think that your users could benefit from really specific messages, then I would use static assert in these classes that are used as containers for static asserts, and bring that type containing the static assert to the API border. And the last item is experiment with concept slide. There is a version out there as a GCC branch. Experiment with it, give feedback to Andrew Sutton and the other developers of that. Help them to do that, or help other compilers to start development on concept slide, because concept slide are going to change the world. They won't invalidate anything of this, but they will change the world for our template metaprogramming experiences. All right. That's it. Questions?
Hi. So in those cases where you have some methods which you don't really define, the overloads that are like wrong using the false type, that you don't define. Have you tried using delete, like deleting them? Maybe that will help, produce better compiler messages or catch some errors earlier. Or in some other cases, have you tried delete?
I haven't tried delete, but I would assume that compilers tell you that this function is deleted, which would give you some more information that you care about. Because then, I mean, the user will will then wonder, okay, why is it deleted? Is it just to produce or to produce this kind of message, or is it deleted because of some error? Is it a mistake of the user that he runs into a deleted message, method? I don't know. I wouldn't do that, but I haven't really tried it.
More questions?
This one here.
Well, it seems like in the last example you showed, you could just implement empty templated where and all the other clauses on the bad statement type, and then it wouldn't give you the last message the last error that you didn't want. Had something like bad statement doesn't have a member where.
Yes, in theory, yes, I could. That would require a lot of additional code, I think, because of the way that the library constructs statements. I have to think about it. It's a good idea. Thank you.
Okay.
Oh, just one more thing. Then, okay, then the where method would have to return something that could still handle the follow-up calls, because there might be having and limit and so. But yeah. Okay. Cool.
As you have shown, the compiler error messages vary between the two compilers you tested, and in my experience, the error messages even change when the compiler version changes. So
right.
This whole task is, well, targeting a moving target. What do you think? Should this become more of a standardization thing, so that we could rely on these techniques to work in the compilers and get so that we can program against some standardized behavior for better error messages?
To some extent, that's what's currently happening, right? With Concept Slide, we're going to get language features that enable you to do things that you currently would do with enable if, for instance, and much more powerful stuff even, and a whole range of checks wouldn't have to be done anymore in the manual way that I showed. You could just do them with concepts. And so, yeah, the language goes in a direction where this is easier. Concept Slide has, I don't know how many goals, but one of the main goals is to reduce the amount of template error messages. So, yeah, the work is already done in this direction.
I will have a question. How
Okay.
do you test your error messages? Have you unit test for that or something like that?
Well, not for all of them, but for a continuously growing number of these cases, I have tests which are run in the normal make script. And the test is basically a short piece of code like this that produces an error. You cannot, in the normal compile process, test for static assert. But what you can do is you can check for the compiler output and use, I don't know, grep or whatever in your make tool to assert that, okay, the message that you expect has already has indeed been delivered by the compiler and the library. You could also check for the size of the message. Make sure that it's not bigger than, I don't know, 1K or so, something that more or less fits on the screen. That can be done with unit tests, yes.
More questions? You all are sleeping or still?
Yeah, it's a tough topic for the first talk in the morning.
Then thank you, Roland.